Banana, 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 banana. Welcome to Math 141 Summer 2020 Recitation, Episode 17. Woo! Today, we are doing a little throwback Thursday. You'll recall that we began this summer by putting the fun in function, and today we are sticking with that, and we are putting the fun in fundamental theorem of calculus. We get to learn one of the obviously most important theorems in all of calculus, where we get to connect these two different approaches we've been taking. We've started off by taking derivatives and looking at rates of change, and more recently we've been looking at integrals, using them to find areas under curves. And so today we get to finally put them all together and see how they fit into this giant, beautiful puzzle called calculus. Section 5.4 gets into the fundamental theorem of calculus and how it comes into play whenever we are solving problems. And section 5.5, we look at indefinite integrals and the substitution method. You will oftentimes, in fact, I will refer to it this way, you will oftentimes hear the substitution method referred to as simply U substitution. That is the variable that we most often use when making these substitutions, and so that's how you will most often hear it called. That is how I was taught, and so that is how I plan to brainwash you as well. All right, well, enough talk. Let's get to the math. We've got a good chunk of problems picked out for today, a few of which I think will take quite some time. So I'm going to do one here at the beginning, problem 2, and I'm going to go through this one fairly quickly because I do think that it's important that you see one of these types of problems. But I'm not going to spend a ton of time on this one because there are some trickier ones later on, which I want to have plenty of time for. So here we want to integrate 8 secant squared x dx over the interval 0 to pi over 3. So the first thing that I'm going to do is I am going to pull this 8 out front. Remember, we can do that anytime that we have a constant. So this becomes 8 times the integral from 0 to pi over 3 of secant squared x dx. Okay, well, let me walk you through how I think about this integral. Well, I know that the derivative of tangent, so I know that the derivative of tangent is secant squared, which means then, if we go the other way, this means that the antiderivative of secant squared x is tangent x. That, in fact, kind of gets at this fundamental theorem of calculus relationship, which we alluded to at the beginning here. So since the derivative of tangent is secant squared, that means that the integral of secant squared, or the antiderivative of secant squared, is tangent x. I suppose I should put a plus c here just so I'm 100% honest and consistent. So this becomes 8, times, now I'm going to put this in parentheses, tangent x, and this is the new part now that we're doing these definite integrals. We are going to evaluate this tangent of x from 0 to pi over 3. You'll see slightly different notations for this. I think the textbook just writes at the top and bottom of this right-hand bracket. But the way that I originally was taught was putting this vertical line here. It doesn't matter. Whatever notation you are comfortable with, I think that it's clear enough what we mean here. So, since this is some new notation here, let's refresh ourselves on what this means. What this means is we're going to evaluate this function tangent of x at pi over 3. So it's going to be 8 times tangent of pi over 3 minus, now I'm going to evaluate it at the lower bound, tangent of 0. Okay, so just to recap what I did there, I plugged in my upper bound. Okay, so I plugged my upper bound into my antiderivative. So I plugged in pi over 3 into tangent of x. And then you subtract out what you get whenever you plug in the lower bound. So then I did minus and then I plugged 0 into my antiderivative, so I have minus tangent of 0. Okay, well, we know these things because we are trigonometry superstars. Let me think. Tangent of pi over 3. Well, sine of pi over 3 is root 3 over 2, and cosine is 1/2. So sine over cosine is going to be root 3 here. And at 0, sine is 0 and cosine is 1. So tangent of 0 is going to be 0. And so this just comes out to 8 root 3. All right. So again, I'm not going to spend a ton more time on that here because there are plenty of other problems to work on. But there's a number of these problems at the beginning of this homework assignment, and they're all going to follow this same idea, the same basic technique, where you find the antiderivative. In this case, our antiderivative was tangent. And then you evaluate at the upper bound and subtract out what happens when you evaluate at the lower bound. Okay? So the trickiest part of those will usually be finding this antiderivative. And once you get past that, it's mostly just plug and chug. Alrighty, let us get on to problem 7. I think that we might already be getting into the tricky ones here. There are quite a few of them on this assignment. Okay, so problem 7 says to find the derivative, and we're going to find the derivative in two different ways here. Okay, so let me go ahead and write the function first. So the function is d dx. Well, I guess I shouldn't say find the derivative of, because the d dx already kind of implies that. So find the derivative. We want the derivative with respect to x of the integral from pi to the cubed root of x times cosine of t dt. Okay, and there are two ways that it wants us to do this. So the first way, we'll go ahead and talk about this all the way through before introducing the second way. So the first way it wants us to evaluate this is by evaluating the integral and differentiating the results. The integral and differentiating the result. So this problem is really getting at the heart of the fundamental theorem of calculus, and differentiating the result. So what this means is first, we're going to solve this integral from pi to the cubed root of x of cosine t dt. Then we'll take the derivative of whatever that is. So let's start by focusing on that integral. So we have the integral from pi to cubed root of x of cosine of t dt. Okay, well, we know the integral of cosine. Remember the antiderivative of cosine? The antiderivative of cosine is sine. Okay, it's easy to get that one confused between the positive and negative signs. So then we're going to plug in our bounds, pi and cubed root of x. Okay, the sine of t. And so this becomes, I'm going to get sine of the cubed root of x. And then I'm going to subtract out what I get whenever I plug in my lower bound. In this case, though, sine of pi is 0, so this is just sine of the cubed root of x. Okay, so now we're going to differentiate the result. So we're going to look at d dx of this sine of cubed... Whoop, I didn't mean to change colors like that. Sine of cubed root of x. Okay, well, it's going to be helpful for me in just a minute to rewrite this as sine of x to the 1/3. Okay, so now this is going to be a standard case of chain rule. So first, the derivative of sine is cosine. So that's cosine x to the 1/3. Now I need to differentiate x to the 1/3. And that is, so times, let me see, bring the power down, 1/3. Times x to the 1/3 minus 1 is minus 2/3. Okay, so let me see. This comes out to cosine cubed root of x over, it looks like 3, there are different ways of writing this. I'll write it cubed root of x squared. Okay, so the x to the 2/3 just means take the cubed root of x squared, and the minus means move it to the denominator. So I believe that this is our derivative. Okay. So we just got our derivative this first way. First we evaluated the integral, and then we differentiated the result. The second way, which they want us to do, give me just a second. Okay. The second way of doing it is by differentiating the integral directly. So in this piece, we are going to use the fundamental theorem of calculus. Let me jot down again what it is we're trying to integrate. It is d dx of the integral from pi to cubed root of x cosine of t dt. Okay. So what we want to do in this case, we are going to notice, first of all, that this is the composite of two functions. So what we notice is that if this were just an x up here, if this upper bound were just an x, then the fundamental theorem of calculus would make this nice and easy. However, because it is the cubed root of x, this is actually a composition of two functions. So what this is, this says first, so let me do this. Let f of x equal the cubed root of x. It then follows then that let f of x be this thing, and let g of x be the integral from pi, or rather, let me write, no, that's fine, from pi to x of cosine of t dt. Okay, so what we want then is we want the derivative of, it looks like we're doing g composed with f, because I do f first. G composed with f of x. Okay, well that is just the derivative of g of f of x, right? And now by chain rule, this is the derivative of g, or this is, let me write it this way, g prime of f of x times f prime of x, right? Okay, so let's go ahead first and let's compute f prime of x. Well, f of x I'm going to again rewrite as x to the 1/3. I like writing things in powers like that because it helps me see how to use the power rule. All right, so f prime of x is going to be 1/3 x to the minus 2/3. I'll leave it like that for now. Maybe at the end we'll simplify, but I think we're going to be doing a bunch of algebra here, so we're going to want to leave it for now. So now if I look at g prime of x, okay, well, g prime, if this was just an x up here in the upper bound, then the fundamental theorem of calculus, I'm going to make this really long, and I'm going to write fundamental theorem of calculus, tells us that g prime, so g of x is this integral from pi to x of cosine of t dt, that tells us that that would just be cosine of x. Remember, the fundamental theorem of calculus tells us that we just plug in our bound. We plug in this upper bound. Okay. So g prime of x is cosine of x. Well then, if I go down, that means that g prime of f of x equals cosine, and now I'm plugging in f of x. F of x was x to the 1/3, so cosine cubed root of x. So our derivative then, so d dx of g composed with f of x, d dx of g composed with f of x, we said that that was g prime f of x times f prime of x. Okay, well, g prime of f of x is cosine of cubed root of x times f prime of x, and f prime of x we said was 1/3 x to the minus 2/3. 1/3 x to the minus 2/3. And if we like, we can rewrite this as cosine of the cubed root of x over 3, and again I have x to the minus 2/3, so it's going to be 3 cubed root of x squared. And guess what? Ready for a cute little magic trick? It exactly matches what we got up here whenever we did it the first way. So the point of this problem, it demonstrates kind of the power of the fundamental theorem of calculus. It gives us two different ways of going about doing this, and everything works out exactly the same. I love problems like this. I know Mackenzie loves problems like this. Mackenzie absolutely adores whenever you can do the same thing in two different ways. So I know that she loves that kind of stuff. Next up is problem 10. Problem 10 says find dy dx for, and our function is y equals x times the integral 2 to x squared of cosine of t cubed dt. So we're kind of going to get into the idea of u substitution here. I don't think technically that idea hasn't really been introduced. This is a 5.4 problem, it looks like. And so technically I don't know if that's really been introduced. But in any case, I think that once you've done 5.5 and once you've read through that, I think that you should be in good shape. If nothing else, I hope that this explanation will make some sense to you. So the first thing that I noticed, and this is actually going to be very similar to what we did the last time, in fact, it looks like I'm going to need to use the product rule, right? I'm going to need to take the derivative of this first part, this x function, and then I have this other function over here, which it consists of the integral. If I just had x in the upper bound here, just as before, if I just had x here, then everything would be hunky-dory and we would be in excellent shape. But unfortunately, we do not just have x there, we have x squared. So what I'm going to do to make my life a little bit easier is I'm going to put myself in a situation where I just have a variable there, not a variable squared. So what I'm going to do is I'm going to say, well, let u be x squared. Okay, so all I'm doing is changing variables. Let u equal x squared. Well, then this means that the square root of u equals x, which means that I can rewrite y as y equals, okay, well, in front here I have an x, and I'm saying that x is equal to the square root of u. So y is equal to the square root of u times the integral from 2 Now instead of to x squared, I'm just going to u cosine of t cubed dt. Okay, so all that I did here was I made a change of variable. All right, kind of like whenever we were doing chain rule, in fact. It's a similar idea. So now I'm going to need to do product rule to take this derivative. Okay, so let f of x, let me call it f of u to be consistent with our variables. Let f of u be the function root u, or u to the 1/2. And I'm going to leave some space because in a minute I'm going to compute f prime of u. And I'm going to then let g of u be this integral function. So it's the function, it goes from 2 to u, cosine of t cubed dt. All right, so we're going to take the derivative of both of these functions because we're going to need that for the product rule. So first let's look at f prime of u. Okay, so f prime of u, well, that's going to be 1/2 u to the minus 1/2. Okay. And then g of u, well, that's going to be g prime of u. Well, this is going to just follow from the fundamental theorem of calculus now. This is just going to be cosine of u cubed. Okay, this right here is this fundamental theorem of calculus, FTC. Okay. Now, there is one other detail that we want to account for. We want to account for the fact that we're looking for dy dx. We want the change in y over change in x, but here we've shifted to this variable u, right? So what I'm actually going to do, and you'll have to excuse me for this, I'm going to, do I want to do this now or do I want to do this in a minute? Let me think. I think that we should do this now. Yeah, why don't we go ahead and do this now? So instead of writing f prime of u, let me write it this way. So the derivative of f with respect to x, the derivative of f with respect to x is equal to the derivative of f with respect to u times the derivative of u with respect to x, right? This is chain rule. Chain. So what we have here, this 1/2 u to the minus 1/2 is df du. And then I'm going to multiply that by the derivative of u with respect to x. So du dx is 2x because u is x squared. All right, so that's 1/2 u to the minus 1/2 times, what did I just say? Times 2x. Okay, similarly, why don't I go ahead and rewrite this ever so slightly? So again, I'm going to write dg dx, because again, that's what we're ultimately going to be interested in. That's going to be the derivative of g with respect to u times the derivative of u with respect to x. So dg du is still just cosine of u cubed. And now I multiply by the derivative of u with respect to x, which we just said is 2x. All right, so now let me plug it into product rule. Okay, so I have that y is equal to, so y here is the product of these two functions, right? It's the product of f and g. Oh, excuse me. So, let me go to black. dy dx is going to be equal to, by product rule, it looks like it's going to be f of x times dg dx plus g of x times df dx. Okay, so let's go ahead and plug stuff in. For now, I'm going to go ahead and plug in f of u. We'll go ahead and make that substitution in a moment to turn this back to x. Okay, we're going to need to change this back to an x in a minute, but that won't be a problem. Times the derivative of g with respect to x. Well, we just computed that. That is cosine of u cubed times 2x. Again, we'll substitute in for all the u's in just a minute. Remember, at the end, we can't have u's and x's floating around. We're going to want everything to be in terms of x, since this is asking for dy dx. Okay, now g of x, well, again, I only have g of u right now, so I'll just go ahead and plug that in. 2 u cosine t cubed dt. And then multiply that by by df dx, and that was 1/2 u to the minus 1/2, 1/2 u to the minus 1/2 times 2x. Okay, great. Okay, so let's go ahead and start making these substitutions. Well, u is x squared, which means that u to the 1/2 is just x. In fact, we already wrote that out down here. The square root of u is x. So u to the 1/2, I'm just x, times cosine. Okay, well, u cubed, that's just x to the 6th, times 2x. Plus, okay, this integral, let me see, so that's going to be the integral from 2 to x squared cosine of t cubed dt. I think we're going to want to deal with that in just a minute. But for now, let's continue making our subs. Times 1/2. I have u to the negative 1/2, so that's going to be u to the 1/2 is x, so I'm going to divide by x now, times 1/2x times 2x. All right, let's go ahead and simplify a bit more. This 1/2x and 2x over here is going to cancel. And let me see, over here, I have 2x squared cosine x to the 6th plus the integral from 2 to x squared cosine of t cubed dt. Give me just a minute. I'm not entirely sure if they want us to evaluate this integral. No, it doesn't look like they do. Okay. Yeah, they don't want us to evaluate this integral. So this is exactly what we finish with. This is what they want. In fact, that integral, that cosine of t cubed, looks like that would be quite a difficult integral, even from a calculus 2 perspective. So I'm glad that we don't have to work that out here. Okay, so what we did here was we applied product rule. We made this u substitution, right? So we started really with this u substitution at the beginning. That made it a bit easier for us to apply the product rule. And in doing so, we needed the chain rule as well. We had to make a bunch of substitutions along the way. I should say that the order in which I made some of the subs, for example, here, if I had left here, if I had just gone, what am I trying to say? If instead of plugging in f of u here at the start, right, so here I plug in u to the 1/2, instead of, I could have gone ahead and solved there and made that substitution and made this x substitution. The order in which you make these substitutions isn't super important. The important thing is that by the end, everything is back in terms of the variable that you want, in this case, x. This integral, we have this t in here, but the t is really just a dummy variable. Okay. So that was a fun one. A little bit of foreshadowing in that we got to see a bit of u substitution here in section 5.4. The last 5.4 problem, which we're going to do, is problem 12, where we are going to find the total area enclosed, of the region, oftentimes it says enclosed, of the region between the x-axis and the graph. The x-axis and the graph. Now, there is a very important phrasing here, and that is total area. Total area, that indicates that we must, I suppose I should actually, let me go ahead and give you the function first. I suppose that would be helpful, because then that will put everything in context. Y equals x cubed plus 3x squared plus 2x, and the interval is -2 less than or equal to x less than or equal to 0. So total area, whenever they're talking about that, what they're emphasizing is that we need, so total area indicates that we need to split up the interval over the intervals where f is positive, or y, I guess in this case y, where y is positive, and y is negative. Then we'll integrate over each region and take the absolute value of each of them. Integrate over each interval, perhaps I should say subinterval to make it a bit more clear what I mean. Integrate over each subinterval. Take the absolute values of them, of these smaller integrals, absolute values of integrals, and then add them all up. Add up. The reason for this is that, let me just sketch a quick picture, not even of this function, just as a quick general example. If I wanted to look at, in fact, I think a perfect example would be the sine function. So sine looks like this, right? This is x equals pi. This is x equals 2 pi. So this is f of x equals sine of x. Well, if I wanted to find the area under the curve, the total, what I'm really interested in is I want to find the combined area of these two yellow regions. However, if I just integrated over the entire region, the entire interval 0 to 2 pi, these two regions would cancel each other out because one is above the x-axis and one is below the x-axis. So the integral from 0 to 2 pi of sine of x dx, it does come out to 0. Again, that's because I have these two symmetric regions, one above the x-axis and one below the x-axis, so they cancel each other out. However, clearly the area is not 0, right? We can certainly see that it's bigger than 0. So this doesn't quite get at the problem that we want to solve. So with that said, let's first figure out where our function y, is negative. So where is y positive and negative? That will help us see where we need to split things up. Okay, well, so let me rewrite y down here for us. So y equals x cubed plus 3x squared plus 2x. I'm going to set this equal to 0. So 0. Once I find out where the function is 0, I can use that to help me find the intervals over which it's positive and negative. So 0 equals, and I'm going to go ahead and factor out an x there, x squared plus 3x plus 2. So 0 equals x times x plus 2, x plus 1, which means that y equals 0 at x equals 0, minus 2, or minus 1. Okay? So then if we look at a picture, what I'm going to do actually is I'm going to go ahead and draw our number line. Okay? I'm going to draw a number line, and I'm going to label 0, minus, let me label them in the correct order. How about that? Minus 2, minus 1, and 0. So now I need to figure out, we're integrating over this interval from -2 to 0. So I don't care what's happening to the left of -2 and to the right of 0, because I'm not integrating over that area. However, I do need to determine what is happening over the interval from -2 to -1 and from -1 to 0. To do that, I'm going to plug values into my function. So if I plug in, for example, x equals minus 3/2, which lives between -2 and -1, then I'm going to see that y, let me see. So if x is -3/2, then if I look at this line where I've got it factored, it looks like I'm going to have negative, positive, negative. So that's going to be 2 negatives times a positive. So that's going to be positive. So y is greater than 0 here over this interval. And then if I look at the interval from -1 to 0, let me plug in x equals positive 1/2. And here it looks like I have positive, or excuse me, that should be negative 1/2. It looks like I'm going to have negative, positive, positive. So that is going to be negative. So y less than 0. Okay, so if I sketch a very quick picture with very little detail, -2, -1, that means that my function, again, I don't care about what's going on to the left and right of our interval, so I'm not even going to bother with that. But it's 0 here at -2, -1, and 0. It looks like then it's positive until -1, and then it's negative until 0. Which means that I want to integrate over each of these two regions separately. So the area is going to be the integral from -2 to -1 of x cubed plus 3x squared plus 2x dx. Okay, this is just y. I know it's been a while since we've seen y. That's just y. Plus, now I'm going to integrate over the other interval from -1 to 0. And really, I should be sticking absolute value bars on these two things, because we're going to want them both to be positive. The integral from -1 to 0 of, again, just x cubed plus 3x squared plus 2x dx. Okay, I might go through this part slightly quickly in the interest of time. So to integrate this first one, okay, so I'm just going to use the power rule for anti-differentiation. So x cubed, okay, so I'll stick my absolute value bars here. X cubed is going to become x to the 4th over 4. I'm going to raise the exponent by 1 and divide by my new exponent. Then for 3x squared, that's going to become 3x cubed over 3, which, yes, we can simplify that in just a moment. And similarly, this 2x is going to become 2x squared over 2. I'm going to evaluate all of this from -2 to -1. I know I'm switching up my own notation. I apologize. But again, I hope it's clear what I mean. The second integral is going to be exactly the same. We are just going to evaluate it at different places. So x to the 4th over 4 plus 3x cubed over 3 plus 2x squared over 2 from -1 to 0, absolute value. Okay, well, let me go ahead and simplify ever so slightly. This just becomes x to the 4th over 4 plus x cubed plus x squared, evaluated from -2 to -1, plus, again, absolute value, x to the 4th over 4 plus x cubed plus x squared, evaluated from -1 to 0, absolute value. Okay. Whew. Now I'm going to go ahead and start plugging in my bounds. So when I plug in -1, that's going to give me, I'm going to do this in my head just to save space, because if I write everything out, it's going to take way too much space. So if I plug in -1, that's going to give me 1/4 minus 1 plus 1. So that's just 1/4. So the absolute value of 1/4. Now I need to subtract out whatever I get whenever I plug in -2. Well, let me see. X to the, so that's going to be 16 over 4. That's going to be 4. Is that, yeah, 4 minus 8 plus 4. So 4 minus 8 plus 4. Hey, that's 0. So 1/4, my absolute value of 1/4 minus 0. Now, okay, if I plug in 0, let me see, that's going to give me just a 0. And now whenever I plug in -1, I already plugged in -1 and it gave me 1/4. So 0 minus 1/4. Okay, so let me indicate what I did here. This is x equals -1, x equals 0, or x equals -2 is there, rather. -2. This is x equals 0, and this is x equals -1 again. So whenever I add these two things up, it looks like I'm adding up 1/4 plus 1/4, and I get 1/2. Ta-da! Let's go. My math lab agrees with me. Phew, all right. I have 3 more problems I would love to get through. Let's see how fast and understandable I can go. Oh, this one, okay, this one won't be so bad, I don't believe, but there's a very, very clever trick. But once you see the trick, it is perfectly manageable. We're going to jump into some use substitution. So use substitution. Again, the textbook just calls it substitution, but whenever I say use substitution, that's exactly what I mean. It makes no difference. To find the indefinite integral, so now we're back where we're not plugging in specific bounds, which means that we're going to want to end our integrals in plus c. Okay, so use substitution to find the indefinite integral. The integral is p times p plus 1 to the 5th dp. All right. So to me, the clear thing that jumps out as a possible substitution here is going to be to set u equal to p plus 1. Anytime that we do a u substitution, we're also going to need to find du. And in this case, du is just 1 dp, right? The derivative of p plus 1, that's just 1. So we have 1 times the derivative of p, dp. Okay. So the problem which I'm seeing here is that most often, whenever we do a u substitution, we end up with the derivative. We end up with the problem is we have this p left over here and at the front of our integral, and I don't know what to do with that. Right? Usually what happens is we make a substitution for u. In this case, u equals p plus 1. And then the derivative, du, somehow it is involved with the remaining piece of it, and we're left with something nice and simple. However, that's not the case here, because I have this extra factor of p. But what I can do is I can notice, well, u equals p plus 1. Well, this means that u minus 1 equals p. Right? So what I can do is I can solve for p in terms of u, which means that this integral, once I make this substitution, is just u minus 1, right? Because p is u minus 1. And p plus 1 to the 5th, well, p plus 1 is just u, so that's just u to the 5th. And then I just have this dp, and dp is just du. Okay? So what we're doing here, whenever we're doing this u substitution, I think about it as translating between two languages. I've got this one language in terms of p's and this other language in terms of u's. And so what I've done is I've translated this integral from the language of p's into the language of u's. And this is very nice because now I can just distribute that u to the 5th and get u to the 1st, or excuse me, u to the 6th minus u to the 5th du. Now by power rule, this is just u to the 7th over 7, excuse me, not plus, minus u to the 6th over 6. All I'm doing there is raising the exponent by 1, dividing by the new exponent, plus c, and we're done, right? No. So we haven't done anything wrong yet. We haven't done anything wrong, but you must remember, whenever the problem starts in one variable, you need to end it in that same variable. So in this case, we need to translate back to p's. Need to translate back to the language of p's. It's like an interpreter, right? Like an interpreter for someone. For example, someone who speaks Japanese, if I was trying to have a conversation with them, if we don't translate back into p's, that would be like if I said something to the interpreter, and then the interpreter started talking in English to the person who only speaks Japanese. It's not going to make any sense to them, right? So we need to make sure that we're finishing back in terms of what we started with. And what we started with in this case was p's. So we make the substitution u equals p plus 1. And so this becomes p plus 1 to the 7th over 7 minus p plus 1 to the 6th over 6 plus c. Again, we hadn't done anything wrong here, but we do need to translate back to the language in which we started. This is such a cute trick where we make the substitution. So we make the substitution u equals p plus 1, and then we solve for this extra piece, this p out front, with a little bit of algebra. That is an excellent tool to have in your back pocket. Now let's do problem 21. Evaluate the integral. Okay, so the integral is the integral of x cubed square root x squared plus 9 dx. Okay, so what I'm going to do this time is I'm going to make, so we want to make a substitution here. This isn't one that we can straightforwardly solve, just like some of the other ones. And in this case, the most natural choice of a substitution is going to be this square root here. So I'm going to let u be the square root of x squared plus 9. I should mention, I'm kind of jumping right into these substitutions here. However, it does take some time, even for me, to look at a problem and think through it and figure out what substitution to make. Of course, the more problems you do, the better you get at these things. But it's certainly not immediate. So I'd hope that me going through and doing these fairly quickly doesn't turn you off, in the sense of doesn't make you feel bad if you can't do it right away. That is perfectly fine. You will get better with time. So be patient. Be patient and practice, practice, practice. For example, I should mention this problem here, problem 20, truthfully, I don't know if I ever learned this cute trick, and I didn't see it, so I didn't remember seeing it until last fall when I was TAing for Calc 2. So there's always going to be things for you to learn, things that maybe you missed the first time around. I'm sure I was taught it. I probably just forgot about it. So be patient with it and just keep working at it. Keep practicing. Anyways, so we're going to make this substitution u equal to square root of x squared plus 9. Anytime that we do that, we make a u substitution, we're going to need to compute du. Okay, so let's see, I get 1/2 times x squared plus 9 to the minus 1/2. And then I'm going to multiply that by the derivative of the inside, which looks like 2x because of chain rule. And so let me see, 1/2 cancels with 2, and I just have x over root x squared plus 9. Okay. So now, what, give me just a second. Actually, let me see, let me look at this. I actually think that I might want to take a different approach. Yeah, actually. Let me, excuse me. So it's good to compute d. Sorry, Siri thought I was talking to her. So it's generally a good habit to compute du. In this case, though, another trick which I'm going to use. So that's helpful at du. But what I'm also going to do is I'm going to rewrite that first identity as u squared equals x squared plus 9. Now I'm going to take the derivative of both sides and write this as 2u du equals 2x dx. So this means then that u du equals x dx. Okay. So let me see what. So what this allows me to do. Okay. Why? Yeah, okay. Give me just a second. I need to think about this, actually. This is a trickier one than I anticipated. Oh, okay. I see. So this one is quite tricky. I see the trick now, the other trick. So what I'm going to do, and wow, this is dirty. I am going to rewrite my integral. So I've got x cubed root x squared plus 9 dx. Let me first rewrite this as x squared times square root of x squared plus 9 times x dx. So what I've done is I've moved one of the powers of x from the x cubed to the back end in front of this dx. Why have I done that? I have done that because x dx, this is u du. Now x squared plus 9, this is just u, or square root of that, excuse me. Right, so I see that u du is x dx from this bottom line. Our substitution said that u is equal to the square root of x squared plus 9. So that means, in turn, since u squared equals x squared plus 9, this means that x squared equals u squared minus 9. And I'm going to make this substitution for x squared. So this integral now becomes the integral of u squared minus 9 times u du. And whenever I combine stuff and simplify, I get u to the fourth integral of u to the fourth minus 9u squared du. Okay, so this becomes u to the 5th over 5 minus 9u cubed over 3 plus c. That's just the power rule at this point. U to the 5th over 5 minus 3u cubed plus c. And finally, I make my substitution for u again. So u is square root of x squared plus 9. So this is u. So this is root x squared plus 9 all to the 5th over 5 minus 3 root x squared plus 9 cubed plus c. You could rewrite this a little bit. For example, I could rewrite that first numerator as x squared plus 9 all to the 5/2 power, but I think this will do the job just fine. I apologize. I was a little slow on that one. This was tricky. I looked at it ahead of time and was like, oh yeah, there's this trick that you have to do where you have to do this, I think, yeah, there was a trick that I didn't anticipate needing to use. But we got through it, and that brings us, sadly, to the conclusion of this video with our final problem of the day, which is problem 22. Ooh, I am so excited for this one. This is of the variety, looks horribly scary, but actually is not. Evaluate the integral. So it's the integral of, I have a 3 on top, and then I have 3x plus 4 times ln of 3x plus 4 dx. Okay, so let me tell you why I believe this one is not so scary. This one certainly looks challenging, and it is challenging. I'm not saying it's not challenging. I guess what I'm getting at is that there's a nice trick, and once you see the trick, it's not so bad. However, seeing the trick is, of course, not easy and comes with experience. What I noticed, so notice the derivative of ln of 3x plus 4 is equal to 1 over 3x plus 4 times 3. Remember, the derivative of the natural log is just 1 over the inside. And then I multiply by the derivative of 3x plus 4, which is 3. And that is 3 over 3x plus 4. And what I notice then is I've got this fraction right here is exactly the derivative. So that, the part in yellow, is the derivative of the part in, I did not mean to, is the derivative of the part in green. So if I let u be ln of 3x plus 4, well then du, we just computed it right here, is 3 over 3x plus 4 dx. Which means that this is just the integral of u of let me write it this way first, of 1 over u du. And this, remember, this is the one case where we can't use the power rule because this is u to the negative 1. This is just ln of u plus c. Okay? So we have, yes, this is true. No, it is not a typo. ln of the ln of 3x plus 4 plus c, the natural log of the natural log. Yes, that is a real thing. Yes, it is awesome. I know. And that does it. As always, if there are any questions about how